Something just happened minutes ago at the edge of everything. A signal arrived from more than 24 billion kilometers of dark, and it should not have been readable. The carrier wave was perfect. The numbers inside were not. Rows of data that should have described the space between the stars had collapsed into a meaningless loop, a string of ones and zeros screaming into the void. For the first time in nearly 50 years, humanity's most distant machine was talking, and it was no longer saying anything we could understand. Stay until the end, because the strange recovery that followed would unlock a discovery about the very edge of our home that no one saw coming, and almost no one is talking about yet. To understand why this quiet moment mattered so deeply, you have to rewind the clock more than half a century. In the late spring of 1977, a small team of engineers at the Jet Propulsion Laboratory in California was racing to finish the most ambitious machine humanity had ever tried to build. They called it Voyager, and they were betting that a series of fortunate alignments in the outer solar system would let a single spacecraft do the work of 4 or 5. Now, the window was rare. It would not come again for almost 2 centuries. They had one shot, a single launch, and they poured everything they had into making it count. Voyager 2 left Cape Canaveral first on August 20th, 1977, taking the longer, slower path through the solar system. Voyager 1 followed on September 5th, 16 days later, riding a faster trajectory that would skip the outer ice giants and aim straight for the giants of the inner outer solar system, Jupiter and Saturn. Both spacecraft were built with a candid honesty that now feels almost quaint. Nobody expected them to survive past the early 1980s. They were machines with a planned death date written into their blueprints. What they actually did with that borrowed time became the longest survival story in the history of engineering, and one of the great love affairs between a species and the smallest things it built. Voyager 1 reached Jupiter in March of 1977-9 and rewrote half a century of planetary science in a single flyby. It photographed active volcanoes erupting on the moon, Io, the first confirmed active volcanoes anywhere beyond Earth. It caught lightning storms the size of continents brewing in Jupiter's colored bands of cloud. It found a thin ring around the giant planet no one had ever seen, and it added detail to the great red spot that turned a blurry smudge into a spinning hurricane 3 times the width of Earth. Then, in November of 1980, Voyager 1 swept past Saturn and did it all again. It mapped the rings of Saturn in such fine detail that scientists still pull measurements from those images today. It measured the strange, thick haze of the moon Titan. And here is where the story bends like a river meeting a stone. To get the best possible look at that cloudy orange world, mission planners bent Voyager 1's path north, lifting it above the plane of the solar system entirely. It was a deliberate choice. It was also irreversible. After Titan, Voyager 1 was never going to fly past another planet again. From that moment on, it was pointed at one destination only, the edge of everything. For most of the 1980s and 1990s, Voyager 1 drifted slowly outward through the silent dark, still working, still sending back data, still teaching humanity new vocabulary for regions no human eye would ever see. Its twin, Voyager 2, kept moving through the solar system on its longer arc, eventually flying past Uranus in 1986 and Neptune in 1989, becoming the only spacecraft in history to visit all 4 of the gas and ice giants. Both probes became, almost by accident, the longest-running missions in the history of spaceflight. 2 thin lifelines strung between 2 small pieces of metal, and the people still listening to them from a pale blue dot far behind. There was a quieter truth behind those first launches that almost no one outside the program was ever told. Both spacecraft were built to survive conditions no probe had ever faced: the violent radiation belts of Jupiter, the crushing gravity wells of the outer planets, the freezing cold of deep space, the kind that would kill ordinary electronics in hours. Every gram had to earn its place. Every cushion had to be fought for in budget reviews. Every component that could not survive the trip was cut from the manifest. The goodwill of 100 quiet engineers sat inside every bolt. That same ruthless honesty is the reason both spacecraft are still producing new science for the public record almost 50 years later. Now, return to the moment when the real story, the one most people do not know, began. On August 25th, 2012, Voyager 1 crossed a boundary that had existed in theory for decades, but had never been touched by anything built by human hands: the hull of the heliopause, the place where the constant outward rush of the solar wind finally falters against the pressure of the wider galaxy, the invisible wall at the far edge of our sun's domain. Everything you have ever known, every planet, every moon, every asteroid you learned about in school, every relative you have ever had, every signal your phone has ever received, lives inside that bubble. Beyond it lies something older, colder, and stranger: interstellar space, the thin plasma drifting between the stars, shaped by the Milky Way itself, by ancient supernova winds, by magnetic fields older than our sun. When Voyager 1 crossed that line, it became the first human artifact to leave the bubble, The history books just had to update themselves, and they never finished. Years before Voyager 1 actually crossed the heliopause, the instruments on board were whispering warnings. Strange pressure pulses arriving from the edge of the sun's domain, sharper than expected changes in particle counts at the outermost fringes of the bubble, a thickening of the wall that did not match any old textbook diagram. Something out there was leaning against the sun's bubble harder than predicted. And the closer Voyager 1 crept to that invisible barrier, the clearer the pressure became. There was, in those pre-crossing years, a quiet argument inside the mission team about what those readings actually meant. Some thought the interstellar medium was denser on that side of the sun than the average for the galaxy. Some thought our sun was pushing the heliopause outward, somewhere well beyond where older papers had placed it. A few brilliant scientists on the team admitted openly that they did not know, and that the truth was probably stranger than anything any of them had imagined. Remember this for later, because this is the twist almost no one pays attention to. Right now, you think you know exactly what Voyager 1 started sending back from beyond the heliopause. You have heard pieces of it before in news clips and short documentaries, but you do not know what that meant once the data kept accumulating year after year. And you do not know what years of that single listening post would eventually reveal. Stay with me, because the next part of this story is where the universe stopped matching the picture in the textbooks. For most of the 21st century so far, scientists had built their best models of interstellar space using telescopes parked safely inside our own bubble, pointed outward at a region they could describe but not actually touch. The guesses were educated. The guesses were careful. The guesses were wrong in ways that mattered. The most basic assumption of all, that interstellar space was a thin, quiet, almost featureless void, was the first casualty of direct measurement. Beginning around 2017, the plasma wave instrument in Voyager 1 began detecting a persistent narrow band of vibration in the charged particles drifting past it, not a burst, not a one-time event triggered by a passing solar flare or a passing shockwave. A continuous hum, a faint but stubborn signal that did not fade away with the seasons, did not change as the sun's activity cycled, did not behave like anything the textbooks had on file, almost like the universe was breathing very slowly just out there beyond our front door and had been for unknown ages. It is worth pausing here to remember that Voyager 1 has never been alone in this mission. Its twin, Voyager 2, launched 16 days earlier but took a slower, longer route through the solar system, using its own gravitational slingshots to fly past not only Jupiter and Saturn but also Uranus and Neptune, becoming the only spacecraft in history to visit all 4 of the solar system's giant planets. Voyager 2 crossed its own version of the heliopause in November of 2018, 6 years after its twin, entering interstellar space from a completely different direction. The readings it sent back confirmed, almost word for word, what Voyager 1 had already begun to show: the strange interstellar hum, the hot, turbulent border, the surprising magnetic conversation between sun and galaxy. Having 2 independent witnesses cross the wall years apart, from 2 separate directions, gave scientists something they had never had in any previous mission: a way to confirm that the discovery was real and not a local accident. That hum changed the field. Until Voyager 1, the only way scientists had ever measured the density of the almost empty plasma between the stars was to wait for a violent event on the sun to send a shock wave rippling outward, disturb the interstellar plasma just enough for orbiting instruments to catch a brief glimpse of its density and pressure. That method worked. It also gave only snapshots. Imagine trying to describe an entire ocean by studying it only during storms. The steady hum from Voyager 1 was a continuous trace. It kept recording year after year, day after day, for almost a decade and counting. And what it revealed was that the space between the stars has structure. It has density waves. It has turbulence. It moves. It has weather. Slow, faint, ancient weather, but weather nonetheless, sculpted by the galaxy's own magnetic breath. And scientists still do not agree on what is making it. 2 leading explanations sit in the scientific literature right next to each other, neither yet proven, neither yet ruled out. The first points to thermally excited plasma oscillations, natural vibrations set up as charged particles settle gently into the surrounding cooler medium, a kind of quiet ringing of an enormous bell. The second points to a more subtle phenomenon called quasi-thermal noise, an even quieter mechanism that might one day let scientists read both the temperature and the density of the plasma directly from the hum itself, if they can eventually confirm which model fits the data best. Either way, the conclusion is the same. Interstellar space is not silent. It is humming, and Voyager 1 is the only machine anywhere near it able to listen. And that machine is fading. But wait, the hum was just the overture. The real surprise came from the very thin sliver of space where the sun's domain meets the galaxy's domain. That place, the hull of the heliopause, was supposed to be gentle. A gradual transition, like a tide rolling out, like two oceans slowly mixing and blending over thousands of years. That is what the computer simulations had predicted. That is what most scientists expected. That is not what Voyager 1 crossed through. The actual heliopause was violent. Charged particles in that thin borderline region were slamming into each other at extreme speeds, compressed from both sides by the crushing pressure of the sun's wind pushing out and the crushing pressure of the galaxy pushing in. Temperatures in that sliver of space reached tens of thousands of degrees. Not inside any star, not anywhere near our own sun, just outside the front door of our own world, separated by less than the distance between your hometown and the next one over, in the most absolute sense. Researchers have since begun describing the heliopause as something close to a wall of fire, a violent collision zone where the sun's domain and the galaxy's domain crash into each other at thousands of kilometers every second. To put those numbers into your body, tens of thousands of degrees at the heliopause is hotter in terms of raw particle energy than the visible surface of our own sun. The particles there are moving faster, smashing together harder, carrying more fury per atom than the glowing face of the star that lights our mornings. And yet, there are so few of them out there that a thermometer would still register almost empty vacuum. It is a strange and beautiful contradiction, a near vacuum that punches harder than the surface of a star. That contradiction forced scientists to rewrite whole chapters on how energy, density, and temperature actually behave in plasma physics under real interstellar conditions. There's one more layer to the puzzle, and this is where the story crosses from strange into urgent for everyone alive on this planet. Voyager 1 also measured something everyone had been quietly assuming was not really there, or at least was gentle enough to ignore. Clear indications that the magnetic field of our own sun and the magnetic field of the wider galaxy were not politely separated by the heliopause. They were actively interacting, reconnecting, exchanging energy, touching each other across the boundary in ways no model had predicted to any significant degree. That single finding means the picture most of us grew up with, the solar system as a sealed dome drifting like a calm soap bubble through the galaxy, is wrong. The truth is closer to a magnetic collision, a living negotiated border. Two enormous magnetic systems pressing against each other, trading energy in surges and pulses, depending on the angle at which the sun is moving through the galaxy at any given moment. The cosmic rays Voyager 1 began cataloging on the other side of the heliopause will matter to every future astronaut who ever leaves low Earth orbit. Right now, the people planning the first crewed trip to Mars are relying on models built before Voyager 1 crossed the wall. Those models assumed a slow, predictable ramp down of cosmic radiation once a spacecraft left the inner solar system. The early Voyager 1 results suggest the truth is messier. The transition is faster, the peak of danger is sharper, and the gradient on the far side behaves more like an uneven slope than a clean stair. Translation for any human heading toward Mars, the radiation risk in deep space could be slightly higher than the older chart suggested. Voyager 1 is the only reason we are catching that error now, while there is still time to redesign the shielding. Now return to that cold November morning in 2023, because the breakthrough almost ended before it could be finished. For 5 long months after the first corrupted signal arrived at the Deep Space Network, Voyager 1's science data remained useless. The spacecraft was clearly alive, it was clearly transmitting. Its carrier wave was steady and strong, exactly where it should be, exactly tuned to the right frequency. But every line of scientific code writing on that carrier was scrambled, repeating meaningless patterns the engineers on the ground could not decode. The mission team at the Jet Propulsion Laboratory began a careful, anxious investigation that would stretch over nearly half a year of sleepless nights and round-the-clock watch rotations. What they eventually tracked down was almost absurd in its smallness. A single chip inside the spacecraft's flight data subsystem, a tiny piece of memory hardware the size of a fingernail, had degraded after 50 years of exposure to the very kind of radiation the heliosphere is supposed to help filter out. That one failed chip was responsible for about 3% of the memory used to package the science data before it was beamed home. 3% of a memory bank sounds tiny. In a system this old, this minimal, this fragile, 3% corrupted everything downstream of it. A single speck of rust had effectively locked the entire ship out of its own voice. There was no way to swap the chip. There was no way to fly a repair mission across 24 billion kilometers of dark. The team had to do something almost unhinged. They identified every critical piece of code stored in that corrupted 3% region of memory, broke it down into smaller slices, and relocated those slices into different parts of the spacecraft's surviving memory. They were rewriting 47-year-old software from across interstellar distances, one careful command at a time, with each command taking nearly 23 hours to arrive at the spacecraft and another 23 hours for any confirmation to come back to Earth. One full round trip was almost 46 hours long, A single typo could kill the entire mission, and no one would know until 2 days later. Somewhere in those months, an engineer at JPL typed a command into a console in California, watched the countdown timer start, went home to sleep, came back the next morning, watched eagerly for the answer to come back from beyond the sun, breathed, and tried another slice. They did that dozens of times. They did it without panic, without drama, with the patient stubbornness of people who had inherited a mission older than most of them and knew they were the only ones left who could speak its language. They had to. Nobody else could. Then, slowly, the data began to make sense again. In April of 2024, the engineering data came back first, clean and readable. Weeks later, the full science data followed. The plasma wave instrument resumed its recording of the interstellar hum. The magnetometer resumed its reading of the magnetic field. The story being pulled out of the dark by Voyager 1 resumed, and what that story tells is not yet finished. But here's the part that hurts. The fix bought time. It did not buy unlimited time. Voyager 1 runs on radioisotope thermoelectric generators, 3 small cylinders of plutonium buried deep in the heart of the spacecraft, slowly converting the heat from the natural decay of that element into electricity. Every year, those generators give a little less. Every year, the budget of available power ticks down another small notch. In February of 2025, mission engineers made a first quiet sacrifice. They switched off the cosmic ray subsystem, an instrument that had been measuring the high energy particles of the sun and the galaxy for nearly 50 uninterrupted years, all to keep the rest of the spacecraft alive a little longer. Even with 4 instruments already shut down, the Voyager team has not given up. Engineers at JPL have begun work on an internal redesign of the spacecraft's power management software, nicknamed inside the team the Big Bang Fix. The plan is delicate and unconventional. It would reroute Voyager 1's remaining electricity, saving watts from systems that could tolerate slightly colder operation, and routing them back into a dormant science instrument for one more short observing campaign. It is a remarkable gamble on hardware now nearing 50 continuous years in flight. If the Big Bang Fix works, Voyager 1 might earn one more year of meaningful science before the lights finally go out. If it fails, the team risks triggering the very safety shutdown they have spent 3 years fighting to avoid. Either way, the engineering is being done from the same California building that built the probe almost half a century ago. Less than 15 months later, in April of 2026, they did it again. On April 17th of 2026, mission engineers sent the command to shut down yet another instrument, the low-energy charged particles experiment, a device that had been running for nearly 50 years without pause. That shutdown came only weeks after a routine maneuver caused a sudden drop in the spacecraft's power levels, a drop that nearly tripped an automatic safety system designed to protect the probe. Had that safety system engaged fully, Voyager 1 might have entered a protective low-power mode from which no human being alive today is sure it could ever fully recover. The Voyager 1 mission team described the moment with a flat, honest, almost heartbreaking voice that has become the tone of the entire mission in its final years. Shutting down a working science instrument is not anyone's preferred choice, he said, but it remained the only way to keep the rest of the spacecraft alive long enough to send back one more chapter of the story. Only 2 active science instruments remain on Voyager 1 today. The plasma wave instrument, still listening for that strange interstellar hum, and the magnetometer, still reading the field where the sun and the galaxy press against each other. 2 instruments, 2 surviving listeners, the same 2 that brought back the discoveries every future mission to the heliopause will be built around. Pause for a moment and ask yourself, if you were the engineer at JPL who had to type that shutdown command, knowing it would silence 50 years of unbroken data collection on a machine older than your parents, would you have hit send? Drop your answer into the comments below. This is not a rhetorical question. Real people had to make that call. Real people still are making those calls right now, this year. If Voyager 1 finally falls silent in the next decade, what do we actually lose? Is it just one aging spacecraft, or the first and only direct witness our species has ever positioned at the very edge of the bubble that protects every living thing on Earth? Drop your honest answer in the comments. I read everyone, and so does the team at JPL. Now zoom out with me, because what Voyager 1 is finding is not abstract science happening in some far corner of the universe with no relevance to life on Earth. It points straight back at you and every person you have ever known. The heliopause is not a line drawn on a classroom diagram. It is the actual physical shield that deflects and slows down a portion of the high-energy radiation constantly streaming through the galaxy from some of the most violent events in the universe, including the explosive deaths of massive stars thousands of light years away. If that shield is as turbulent, as energetic, as magnetically tangled as Voyager 1 is showing it to be, then the protective wall our planet sits inside is more complicated and in some ways more fragile than most of the public has ever been told. Understanding that SHIELD will eventually matter for every long-duration mission beyond Earth, for the safety of future astronauts, and eventually for the survival story of the species itself. Voyager 1 is the only reason we know that today. And there is one more milestone approaching that makes every remaining watt feel precious. Sometime in 2026, Voyager 1 is expected to cross a distance so vast that its radio signal traveling at the literal physical speed of light will take a full 24 hours to reach Earth from the moment it leaves the spacecraft's antenna. One full light day. A single command sent from the ground will take a full day to arrive at the spacecraft. The answer, if any, will take another full day to come home. Every exchange from that point forward will cost 2 full days of waiting. No spacecraft currently alive has ever operated while still active and still transmitting from a distance of 1 full light day from its makers. When that moment arrives, the round-trip delay will be longer than the working hours of any human engineer alive on the planet. What makes all of this almost unbearably beautiful is the contrast between the spacecraft itself and what it is still doing. Voyager 1 was designed using technology that predates the modern microprocessor as most people understand it. Its onboard computer has less processing power than a basic musical greeting card. It runs on roughly 200 watts of usable power today, less than what a kitchen blender uses to whip cream. And yet, this almost absurdly primitive machine is still the only object our species has ever positioned beyond the heliopause, the only instrument ever to have crossed the wall and started measuring the other side directly with its own sensors. Every telescope back on Earth, no matter how large, no matter how powerful, no matter how recently built, is still observing interstellar space from the inside looking out. Every computer simulation of the interstellar medium ever built before Voyager 1 crossed was, in essence, an educated sketch of a place no one had visited. Voyager 1 ended the era of guessing, and it is doing so while its power slowly, irreversibly runs out, one instrument at a time. The next generation of interstellar probes is already being sketched in labs from California to Asia. Some borrow directly from Voyager 1's surviving instrument list. Some propose entirely new sensors for reading the interstellar medium faster than Voyager 1 ever could. Whatever shape the next probe takes, its blueprint will almost certainly carry Voyager 1's last measurements inside its planning documents. The spacecraft closest to dying is still, in its final years, the one teaching the rest of us how to listen to the space between stars. And here's the very last layer of the story, the part that still lingers with the people who built the ship. Bolted to the side of this fading spacecraft is one of the strangest and most poetic objects humanity has ever built, the Golden Record. A 12-inch gold-plated copper disc, sealed inside an aluminum case, attached to Voyager 1 before launch, and engineered with the best science of 1977 to remain playable for at least 1 billion years. It carries greetings recorded in 55 human languages. It carries natural sounds from the surface of our planet, thunder, wind, rain, the calls of animals. It carries 90 minutes of music, spanning cultures and centuries. It carries encoded images of human anatomy, of the structure of DNA, of how a woman eats lunch in a field, of how a man plays a flute, of the structure of our solar system and where we sit in the galaxy. The cover of its aluminum case carries symbolic instructions for any future finder, written in a mathematical language intended to be read by anyone with a basic grasp of physics, showing how to play the record and where exactly we are, sitting on a small rock around an ordinary star. 1 billion years. Statistically, the Golden Record will almost certainly outlast every star currently visible in the night sky above your head tonight. It will very likely outlast the sun itself. The only question is whether the science, the quiet signal it represents, the human voice reaching out to introduce itself to the galaxy, will ever finish being sent. That is the deepest part of this whole story, the part that follows you into sleep. Voyager 1 has already outlived almost all of its original designers. It has outlived its prime contractors, its launch teams, its original science leads. Most of the engineers now caring for it were not yet born when it left the planet. It might yet outlive its current caretakers too. And when its final transmitter finally falls silent, whether that day comes in 2 years or 10, the spacecraft itself will not stop. It will keep drifting outward through the galaxy at more than 17 kilometers every second, silently for millions of years, carrying greetings in 55 languages past stars that have not yet been born. There's one final layer that almost no public discussion of Voyager 1 ever reaches. And yet, it is the layer that pulled the mission into existence in the first place. Humanity has never asked a question more honestly than this one. Are we alone? Are we the only small accidents of chemistry that ever stood up and looked out and wondered? Voyager 1 was launched before the universe gave a clear answer, and it was launched without any guarantee that an answer would ever come. The Golden Record on its side is the physical form of that same question. If something, someday, somewhere in the long dark, finds it, the record is asking the same question we have been asking ourselves since we first looked up. And now Voyager 1 is asking it one more time, in the language of plasma waves and magnetic fields, right at the threshold of the answer. Thank you for staying with me on this one. If stories like this keep you awake at night in the good way, subscribe to Galaxy Sphere and turn on the bell so you do not miss the next chapter. We are going to keep chasing the biggest questions the universe has hidden from us, while the only machines that have ever answered some of those questions keep slowly falling quiet. Drop a comment below and tell me what you would put on the next golden record if you were in charge of the next message. I will read every single response. Until next time, keep looking up.